Welcome to the second lecture of EE501 of this week. So remember, in the last lecture I made a review and started with the two questions of AX equals to B. So the questions that we asked were, does there exist a solution, an exact solution? And the second question was, if there exists a solution, or when there exists a solution, exact solution, then is the solution unique? And we gave the answers of these questions based on range space of A and null space of A. In the second lecture, I'm first going to start with a review again and remind the main points that we are going to use in this lecture. And then we are going to see two topics, which is the minimum error solution and the minimum norm solution. So remember, if I start with AX equals to B, suppose that X is in Cn and B is in Cm, and suppose that A is in C n by n. Okay, so A is an n by n matrix, and we would like to find X, A, and B are given. So in this case, remember, A is a linear transformation, and it has a domain V and codomain W. And what are these sets? The domain is Cn, and it is n-dimensional, and the codomain is W, and it is Cn, and it is n-dimensional. So remember, we have seen our subspaces in this domain and the codomain. Remember, null space of A is a subspace of Cn, the domain, and range space of A is a subspace of the codomain. All right? So we are going to use, and A is a linear transformation in between these spaces. And remember, null space of A is a set of all vectors in the domain which are transformed by A to the zero vector. And range space of A are the set of vectors in the codomain for which I can find an X in the domain which is transformed to that vector in the codomain. Okay, so remember, you have seen the fact that any space can be decomposed into one of its subspaces and its orthogonal complement. Okay, so you have seen this fact, and this meant that any vector V, here this V does not really have to be the domain, so it is a general subspace. So I can choose my V as the codomain here. In that case, it's going to be Cm. If I choose V Cm, then it's going to be my V. And this means that I can write any vector V in capital V as a sum of two vectors, V1 plus V2, where V1 is M and V2 is in M orthogonal complement. And I know that V1 and V2 are unique. It is what this circle means. And I know that V1 is orthogonal to V2. It is what this orthogonal sign, perp sign, means. And when we have this type of property, we can actually say that the projection of V onto M is V1, and projection of V onto M orthogonal complement is V2. These are the unique orthogonal projections. And since this is a direct sum decomposition like this, I can actually write dimension of M plus dimension of M orthogonal complement is equal to dimension V. So when I look at a direct sum decomposition, there is no redundant dimension here. Summation of the dimensions of these two subspaces. Here it really doesn't matter if we have an orthogonal direct sum decomposition or not. In a direct sum decomposition, if I sum the dimensions of the individual subspaces, then I would get the dimension of the direct sum subspace. Okay, so we have this type of relationship. Remember, we also have between a rank nullity theorem that is given like this: dimension of range space of A, dimension of null space of A is equal to, in this case, this is going to be the dimension of the domain here, and domain here is Cn, which is n-dimensional. All right, so that is what this rank nullity theorem means. Dimension of range space is our rank, and dimension of null space is called nullity. in the linear algebra. Okay? We are going to use this rank property, dimension of the range space of a matrix. We are going to define what rank is, and we are going to see that it has a very, very specific property in the future. So now these are some things that I wanted to review here. So now we are going to start with our main topic. So remember, we have seen that the equation Ax is equal to b has an exact solution if and only if b is in range space of A. Okay? We have seen this fact. But in general, when usually this A and B, or only B sometimes, are obtained by using some measurements, and sometimes, in many cases, this B is not in range space of A. Okay? In that case, we really do not give up immediately. In general, we would still like to, if B is not in range space of A, then no exact solution if B is not in range space of A. In that case, as I told you, we really do not want to give up. We would still want to find an approximate solution in some sense. In some sense, in that case, would mean a very, very specific thing in this course, but in general, you can change that in some sense and obtain infinitely many different solutions for Ax equals to B, even when B is not in range space of A, using different approximations. So in this case, we go for a best approximation. We go for in some way a best approximation. Okay? And in this course, this best approximation means the solution of the following optimization problem. Minimize x with respect to x, the norm Ax minus b. Okay? So Ax minus b is called the error. So we want to minimize this cost here, and the x set that minimizes this cost function actually becomes our minimum error solution. In general, the minimum value of this function is shown by mean with respect to x of this. Okay, so this is the minimum value of the function that we would like to minimize. So if x is lying on a line, then maybe I should draw it in a better way. So if this is my cost function, then the minimum value is given by this expression. And what about the x hat value that would give me this minimum value? It is then called as the argument of the minimization, okay, with respect to x of the cost function Ax minus b. All right? So argument of minimization. So this value, the minimum value of the function is this value, which is obtained at the minimum value of the function. The x value at which this minimum value is achieved is the argument of the minimization, and it is defined like this. So we would like to find an x hat value that would minimize this error. So x hat is called the minimum error solution. Okay, that is the name of such a solution. And depending on the null space of A, this minimum error solution can be unique, or there can be infinitely many minimum error solutions. And we're going to see what we are actually going to do when the minimum error solution is not unique. So here let us try to look at this optimization problem. So we would like to minimize the norm of this error here with respect to x. All right, and I would like to call the x set value which would achieve this minimum as my x set, which is the minimum error solution. Okay. So here is what I'm going to do. I'm actually going to take V is equal to Cm, and this is range space of A. And I'm going to take M equals to range space of A, and M orthogonal is going to be range space of A orthogonal complement. All right, and then I will try to make this decomposition. All right, and then I'm going to use that decomposition to obtain the solution of this optimization problem. Okay, before that, suppose that I have this minimization problem, and suppose that B is in range space of A. In that case, what would you expect for this minimum to be? Suppose that I would like to calculate this minimum error, the minimum value of this error, and suppose that B is in range space of A. What would you expect this minimum to be? Obviously, the minimum is going to be 0, because if B is in range space of A, then I can find an exact solution. As a result, and that exact solution is going to be my x set, or one of the exact solutions will be my x set. And then, since the equation is satisfied exactly, this error is going to be equal to 0 at that x set value, and the minimum error is going to be equal to 0. Okay? If B is not in range space of A, then obviously this minimum will not be equal to 0. It's going to be a positive number. And then our x set needs to be calculated in a specific way. So here is what I'm going to do. I will choose my V in that theorem, choose my V as Cm, the codomain of the linear transformation, the matrix A, and I will choose M as the range space of A. Okay? And that tells me that V, which is Cm, is equal to range space of A plus range space of A orthogonal complement. Okay? And I know that when I try to calculate this error, B is not in range space of A. Otherwise, this minimum is 0, and I don't really want to calculate it. So when B is not in range space of A, then that means that, and B is in Cm, I can actually write B, which is in Cm, in terms of two vectors, summation of two vectors, B1 and B2. This B1 is in range space of A, and this B2 is in range space of A, orthogonal complement. Okay? And of course, these B1 and B2 would be unique, and B1 would be orthogonal to B2. All right? So I have these properties coming from that theorem. Now I'm going to be looking at this cost function, AX minus B. So instead of minimizing this cost function, I can actually minimize its square, because this is always a non-negative cost function. Norm is always non-negative. Therefore, instead of minimizing the norm itself, I'm going to minimize its square. It really doesn't matter, because norm can never be negative. Okay? And then I'm going to use the property of the norm, relating it to the inner product. And inner product is going to be important because of this orthogonality properties. B1 is orthogonal to B2. Okay? So here AX minus B is equal to, the square is equal to, I have AX minus, instead of B I will write B1 minus B2, okay, square. And now I can use the property, this is L2 norm here, and I'm going to use the L2 inner product property. AX minus B1 minus B2 inner product with itself. AX minus B1 minus B2. Okay? Norm square, since we are thinking about L2 inner product, this norm square is equal to the norm square of a vector is the inner product of a vector of the vector with itself. All right? Now let us look at these vectors. I am trying to minimize this with respect to x. So x is the optimization variable here. B1 is in range space of A. B2 is in range space of A orthogonal complement. And what about AX? We know that AX is a linear combination of the columns of A. Okay? Remember, I did this in the last lecture. AX is A1, A2. These are the columns of A. AN times the components of X, elements of X. And this is nothing but a linear combination of the columns of X. And if a vector is a linear combination of the columns of the matrix, then it is going to be inside range space of A. So whatever I choose as my X here, this AX is going to be in range space of A. Okay? So of these three vectors, two of them are in range space of A, and one of them is in range space of A orthogonal complement. Okay? And what about AX minus B? AX is in range space of A, and B1 is in range space of A. So AX minus B1, where should it be? I know that range space of A is a subspace. Okay? Which means that it is closed under addition operation, or under subtraction operation as well, because it is closed both under addition and scalar multiplication. It is closed under subtraction. That means that AX minus B should be an element of range space of A. Okay? So I have AX minus B1 should be an element of range space of A. So the first vector here, AX minus B1, is inside range space of A. And the third vector, B2, is in range space of A orthogonal complement. Now I would like to put some parentheses here on the around AX minus B1. And then I will distribute this inner product. Inner product, it can be distributed with respect to addition, with respect to both arguments, okay? First and second argument. So I can write here AX minus B1 and AX minus B1. Remember, I'm trying to minimize this cost function with respect to x, okay? And I have plus, or maybe I should put minus here, minus AX minus B1 and B2 minus B2 AX minus B1, and I have finally plus B2 B2. Okay? So you see that I have four terms. Now these vectors AX minus B1, they are both in range space of A, and here AX minus B1 is in range space of A, but B2 is in range space of A orthogonal complement. So that means that these two vectors should be orthogonal to each other. Whatever I choose X, these two vectors, inner product of these two vectors should be 0. So this is 0. What about these? So I have B2 AX minus B1. B2 is in range space of A orthogonal complement, and AX minus B1 is in range space of A. That means that these two vectors should be orthogonal to each other. Okay? So which means that this cross inner product is also equal to 0. So we end up only the first and the fourth terms here. Okay? And what about this? AX minus B1, AX minus B1. I know that this is AX minus B1 norm square. Okay? Plus, I have B2, B2, which is going to be B2 square. All right? So this is the cost function that I would like to minimize. AX minus B square. And that is going to be important for us. So now I would like to minimize this. So I have AX minus B square is equal to AX minus B1 square plus B2 square. Now I see that between these terms, only one of them is dependent on the optimization variable. So only this term is dependent on the optimization variable, and the second term is always a constant. Okay? So that means that whatever I choose, this x here, because this norm is going to be non-negative, this ax minus b squared is always larger than or equal to b2 squared. Okay? Because this norm square is always non-negative, that means that this function that I would like to minimize is always larger than or equal to b2 squared. Whatever I choose my x, whatever I choose my x value or x vector, this norm square that I would like to minimize is always larger than or equal to b2 squared. Okay? So now the question that I would like to ask is that by choosing a specific x, can you reach this lower bound? This b2 squared is a lower bound for our function, okay? And I'm asking you here that by choosing an x, a very specific x, can you make this inequality equality, okay? Can you turn this inequality into an equality, okay? By choosing a very, very specific x. So how can this number be equal to this b2 square? Obviously, if this norm square, the first norm square is equal to 0, then I can actually make the inequality an equality. Okay? So in that way, I can actually minimize this function. All right? This function. And can I make this norm equal to 0? Let us think about it. So I have ax here, and b1 is in range space of A. Okay? So by choosing an x, can you make this norm equal to 0? The answer is going to be actually yes here, because since b1 is in range space of A, I can actually find an x which would satisfy the equation ax equals to b1 exactly. There exists an exact solution to the equation ax equals to b1, okay? And that is going to be minimizing this cost function, and the result of the cost function will be equal to b2 square, b2 norm square, okay? So then what is x set? X set would be, which is the mean arc mean, with respect to x, ax minus b, which is this one, it is going to be the solution, or a solution, let us say, because there might be many solutions, a solution of the equation ax set equals to b1. Okay? This is my x set. And what about minimum value ax minus b with respect to x? And this is going to be this minimum value, which is going to be b2 norm square. So you see that by using the arguments from the projection theorem, which was based on that theorem, we are able to find the minimum error solution as the solution of another equation, another ax equals to b equation, which always has a solution. Okay? Why it always has an exact solution? Because b1 is in range space of A now. Okay? That is why this equation always has an exact solution, and such an exact solution would be the minimum error solution, and the minimum value of the error that would be obtained by this solution would be the norm of b2 square. Okay? So let us say, and x set is called the minimum error solution. I was going to write the same thing. So this is just our theory, and now we would like to use this theory to obtain some solutions which do not have exact solutions. Some solutions for some equations which do not have exact solution. Okay, let us say example. And in this case, I will solve the question that we started with for the topic here. AX equals to 2, 1. Okay. So I have this question, and now range space of A, let me write it here, is equal to span of 1, 1, and definitely 2, 1 is not in range space of A. Okay? And as a result, this equation really does not have an exact solution. But what about an approximate solution? An approximate solution in the sense of minimum error. Okay? In this sense given by this equation. And now what I'm going to do is to find B1. Okay? So remember here, B1 is, if when I take this B, and if I write this in terms of B1 plus B2, and then B1 is going to be the component of B in range space of A, and B2 is going to be in range space of A orthogonal complement. So remember what I said about such decompositions. When I decompose V as the sum of V1 and V2, and this V1 is in M, and V2 is in M orthogonal complement, I know that V1 is nothing but the projection of this V onto V1. Okay? Onto M. So sorry. So V1 is nothing but the projection of V onto M, and V2 is nothing but the projection of V onto M orthogonal complement. And while trying to derive this theory, we use the following decomposition. Cm is range space of A, orthogonal direct sum, range space of A orthogonal complement. Okay? So we write B is equal to B1 plus B2. B1 is in range space of A, and B2 is in range space of A orthogonal complement. Okay? Then what is this B1? B1 is nothing but projection of our B vector, which is not inside range space of A, onto range space of A. Okay? And what about B2? B2 is a projection onto range space of A orthogonal complement B. All right? And as a result, that means that in order to be able to find B1, I can use the projection theory. Okay? And how can I actually project B, this B, onto range space of A? By using the theory that you have developed in the topic of application of projection theorem onto Cn. Okay? In that case, we know that B1 is equal to projection onto range space of A, and I have B, and we know that this is going to be a matrix multiplication, P range space of A times P. And this P range space of A is going to be the so-called projection matrix. P range space of A is equal to B Hermitian B inverse, B Hermitian B, where B is the matrix composed of the basis vectors for the subspace that you would like to project onto. Okay? Now, how should I choose my B? The range space of A that I would like to project onto is one-dimensional. Therefore, it has one independent basis vector. So that means that I will choose my B to be composed of columns, a single column, 1, 1. If range space of A had more vectors in its basis set, then I would put those vectors also into my B matrix. Okay? But in this case, we have only a one-dimensional range space. That means that B is just going to be a column vector. Okay? It's a single basis vector. So here, everything is real here. Range space of A is real. So Hermitian can be turned into a transpose. So I have B transpose B inverse times B transpose. Okay? So when everything is real, Hermitian operator, which is the complex conjugate transpose, turns into the transpose operator only, because conjugate will be itself. So here let us calculate B transpose B, which is 1, 1. This is B transpose, and B is 1, 1. So that is going to be just 2. All right? And B transpose B is therefore a scalar, which means that its inverse is 1 over 2. B transpose B inverse is equal to 1 over 2. Okay? Now I can actually calculate here this matrix. B is 1, 1 times 1 over 2, B transpose B inverse, and I have 1, 1, which is B transpose. And that is going to give me 1 over 2, 1 over 2, 1 over 2, 1 over 2. So this is my projection matrix in this case. Okay? And I can obtain B1 by projecting that B onto our range space. Okay? By multiplying with that matrix. All right? So B1 is projection matrix times that B, which is 2, 1. Okay? And this is going to be just 3 over 2 and 3 over 2. Is this inside range space of A? It has to be inside range space of A, because we made a projection onto range space of A, and that is the closest vector inside range space of A to this vector. And now I can obtain my minimum error solution by solving the following equation. AX set is equal to B1. All right? And here, my A is 1, 1 times X hat. And that is equal to, my B1 is 3 over 2, 3 over 2. Okay? And we see the solution of this equation quite easily. X hat, the minimum error solution is 3 over 2. Okay? And what about the value of the minimum error? What is the minimum error that we can achieve? And in that case, it was just B2. Okay? It was just norm B2 square. This is the minimum. So if you are trying to calculate this, so this is minimum AX minus B. Instead, I don't have any square now. Then this is going to be norm of B2. Okay? What is B2? B2 is the projection of B onto range space of a orthogonal complement. Okay? So you can actually try to calculate, find the basis vectors for the range space of a orthogonal complement. It is going to be, for example, 1 and minus 1. And then instead of this B, use 1 and minus 1, and then calculate B transpose B inverse, and use this formula to calculate the projection matrix, then multiply it with B to calculate B2. But is this really necessary? How can you calculate B2 in this case more easily? And the answer is really simple. I know that B is equal to B1 plus B2. And we know what B is, 2, 1. And B1 is 3 over 2 plus B2. And that is going to give you what B2 is automatically. Okay? So if you subtract the projected vector onto range space of A from the actual vector, you will get the projection onto the orthogonal complement of range space of A. Okay? Then B2 is going to be here. This is 4 over 2, so I have 1 over 2, and I have minus 1 over 2. Okay? This is the projection of 2, 1 onto range space of a orthogonal complement. And your answer, therefore, the minimum error is going to be just 1 over 2 minus 1 over 2 norm. Okay? And we know what this is. This is square root. I have 1 over 4 plus 1 over 4. And that's it. Okay? That is our minimum error for this approximate solution. And there is a final question that I'm going to ask here. Is this solution, is this minimum error solution unique? That is our question. We have calculated the minimum error solution, and is this solution unique? It all depends on the null space of A. So I have here AX set equals to B1, and I have found X set which satisfies that equation, and uniqueness of that solution is dependent on here what the null space of A is. And for this example, null space of A is just a zero subspace, a zero-dimensional subspace. That means the solution is unique. So X set is equal to 3/2 is the unique minimum error solution. Error solution. Okay? So that completes our theory. So when we have an equation Ax equals to B, which doesn't have an exact solution, we might go for an approximate solution. An approximate solution means the solution which minimizes a form of error. And in this case, we have defined our error as the L2 norm of Ax minus B. Okay? And minimizing it will give you a minimum error solution. And in this case, that minimum error solution is unique. But of course, if A had a non-zero null space, a null space which has non-zero vectors in it, then in that case, this minimum error solution would not have been unique. Okay? So now let us go back. Let us go to the other example that I would like to show you. So remember here, I showed you another example which was looking like this. So I had 1, 1, 2, 2, and I have X, and I had 2, 1, which had a form like this. And in this case, we have calculated range space of A to be the same span of 1, 1. In this case, I had 2 columns, but the span of those 2 columns is only one-dimensional because these 2 columns are linearly dependent. Okay? And that is range space of A. And we have calculated actually also the null space of A here. And it was span of 2 minus 1. Okay? And both were one-dimensional spaces, and their dimension summation would be 1 plus 1, 2, which is the number of columns of this matrix, the dimension of the domain of the matrix. Okay? Now we know that this B is not in range space of A. Okay? So I have 2, 1 is not in range space of A. This is my A. That means that in order to be able to find, that means that I cannot find an exact solution, but I can go for an approximate solution. And that means that I need to project this B onto range space of A. But this is exactly the same problem. Range space of A was the same here, and B was the same. That is exactly the same problem. So here B1 is nothing but 3/2, 3/2. Okay? And now in order to be able to find the minimum error solution, I can actually substitute this B1 instead of B. 1, 1, 2, 2, X is equal to 3/2, 3/2 here. Now this is going to be X set. This is not going to be an exact solution, but it is the minimum error solution. So this B is in range space of A now. That means I can definitely find a solution here. What can be a solution? X set is equal to, for example, 3/2 and 0 is a solution. Are there more solutions? The answer is yes, because null space of A is not composed of only the 0 vector. There are non-zero vectors in the null space of A. That means that I would have infinitely many solutions in this case. Another solution, for example, X set is equal to 0 and 3/4 here. Okay? And I can find definitely infinitely many solutions. So then the difference of these solutions would give me, so both of them are minimum error solutions. They would result in the same minimum error, but that is actually saying us that the minimum error solution is not unique. Minimum error solution in this case is not unique. So we have infinitely many minimum error solutions. And now what to do in such a case? In such a case, as I told you at the end of the last lecture, we are trying to look for a solution with the minimum norm. So there might be some other criteria to select a unique solution, but in general what is done in linear algebra, in mathematics, is the case of the minimum norm solution. So I would look for such x set values, and I would try to find the one which would satisfy this equation exactly, but with the minimum norm. In this case, the norm of this solution is 3/2. If you take the L2 norm of this solution, it's going to be 3/2, and this is 3/4. So instead of this, I would try to select this one. But I can ask the question, are there other solutions with smaller norm than this one, for example? And actually, we are going to see that the answer is going to be yes. The minimum norm solution, minimum norm, minimum error solution is not this one. We are going to see that it is going to have non-zero elements for both elements of X set. Okay? So now we finished the issue of existence of solutions, and we have seen how we can find an approximate solution. And now we're going to solve the uniqueness issue. Suppose that X hat is any exact solution of AX hat is equal to B. Here I can here put B1. It really doesn't matter. So of course, to have at least one solution, I need to have a vector here, which is an element of the range space. And here, in this case, let us say that M is an element of null space of A. Okay? Then I'm going to ask the following question. Is X set plus M, this vector, another solution, another exact solution? Okay? And the answer to this question, as we did in the last lecture, is going to turn out to be yes. So how can I understand if this is an exact solution or not? Okay? I can actually try to look at if this X satisfies this equation times A is equal to, if the right hand side gives me B1, then I'm done. Okay? So I have, this is AX set plus AM. And AX set is, by the property of this exact solution, is B1, and AM is going to be equal to 0 because M is inside the null space of A. Okay? Plus 0, and that is B1. So that means that if X set is an exact solution, X set plus M is another exact solution for any M is in null space of A. Okay? For any vector is in null space of A, X set plus M is another exact solution. Okay? If X set is an exact solution. Okay? So what do I need for X set and X set plus M to be the same solution? In that case, I would need M to be only equal to 0. If M is only equal to 0, then x set and x set plus m will be the same solution. And actually, if null space of A is only composed of 0 vectors, then x set is going to be the unique solution. Okay? On the other hand, if null space of A contains some non-zero elements, then x set and x set plus m can be different, so there will be infinitely many solutions. Because in null space of A, there would be infinitely many non-zero vectors. So now I would have to erase this, but we will come back to this question and we'll calculate the minimum error, minimum norm solution later. But now I would like to work on the theory of minimum norm solution. So in the case of non-uniqueness, we look for the solution with minimum norm. Okay? So what does this mean? We are trying to solve the following minimization problem. Suppose that there exist exact solutions, but there are infinitely many of them. In this case, I will write this as Ax equals to B. Suppose B is inside range space of A. And in that case, and if null space of A is not really only the zero subspace, then there would be infinitely many solutions to this equation. And what we try to do is just this. Minimize the norm of X over all such vectors which would satisfy this equation exactly. Okay? Minimize norm of X over such X vectors that would satisfy this equation exactly. So this is the minimum value of the cost function. The X value that would obtain this minimum, let us say that this is argument of this minimization, Ax equals to B, X, I will call it as X set 1. Okay? And this is going to be called, the minimum is called minimum norm solution. Okay? And now we're going to solve this optimization problem by using the theory that we have learned with the projection theorem. Okay? Remember, in the minimum error case, I actually decomposed the domain into range space of A and the range space of A orthogonal complement. In the minimum norm case, I am going to decompose the domain. In the earlier case, I decomposed the codomain into range space of A and range space of A orthogonal complement. And now I'm going to decompose the domain into null space of A and null space of A orthogonal complement. Okay? And let us see what we can do. So here, how can I express all solutions of this equation? Okay? Suppose that X set is an arbitrary solution of Ax equals to B. Arbitrary exact solution. Okay? Therefore, I know that A times X set is equal to B. This is an exact solution. Okay? Then how can I parameterize all of the different solutions of this equation? I can actually write all solutions of this equation in the following form. X is equal to, this is an arbitrary solution, plus M. Well, M is any vector inside the null space. Okay? So now what I would like to do is to solve this optimization problem. Minimize Ax equals to B, X. I am minimizing the norm of X over all X's which would satisfy this equation. But I know that all such x's can be written as an arbitrary solution x set plus a vector inside the null space. So instead of this optimization problem, I will write the following. Minimize when m is inside null space of A, x set plus m. Okay? I know that any solution or any exact solution of this equation can be written as an arbitrary solution plus an element of null space of A. Okay? And now I can replace this x with x hat plus m. Now instead of making my optimization over x, I try to optimize m. Okay? The solutions of these two optimization problems would be the same. So now instead of solving this one, I will try to solve this one. Okay? And where x hat is an arbitrary solution, arbitrary exact solution to this equation. All right? So now here is what I'm going to do. I will, x hat is a solution, therefore it is inside Cn. All right? Because the x's are in Cn. All right? And I know that I can decompose Cn into two subspaces. One subspace and its orthogonal complement. Now what I'm going to do is I will choose M as null space of A orthogonal complement, and I will choose M orthogonal complement to be the null space of A. So I can write Cn, let me write it first like this. So now I don't want this decomposition. In this case, M is null space of A, and M orthogonal complement is null space of A orthogonal complement. So I don't want this decomposition, but I want to exchange this. It really doesn't matter. Cn is equal to null space of A orthogonal complement, orthogonal direct sum, null space of A. Okay? This is the reverse decomposition. I just changed the order of the vectors v1 and v2 here. Okay? So since x hat is in Cn, using this decomposition, I can write x hat in terms of two vectors. x1 hat, which is going to turn out to be that solution actually, and I have x2 hat. Okay? And x1 hat here is in null space of A orthogonal complement, and x2 hat is in null space of A. Okay? So now let us go back to the optimization problem. I would like to solve this optimization problem. So I would like to minimize x hat plus m. X hat is an arbitrary solution of this equation, exact solution of this equation. And I have the decomposition of x hat given by x1 hat plus x2 hat. All right? So now instead of minimizing this cost, by choosing an m in null space of A, I can minimize its square again. Okay? It really doesn't matter because the norm is non-negative. That is equal to, instead of x hat, I will write its decomposition. x1 hat plus x2 hat plus m square. Now let us look at these vectors. M is in null space of A. In the optimization, I need to choose M in the null space of A for x hat plus M to be an exact solution to this equation. M is in null space of A. X2 is in null space of A. And x1 hat is in null space of A orthogonal complement. All right? Now let us go into the inner product domain. This is L2 norm squared. That means that this is the inner product of the vector inside with itself. x1 hat plus x2 hat plus m, and x1 hat plus x2 hat plus m. Now x2 hat and m are both in null space of A. since null space of A is a subspace, their sum should also be inside null space of A. Okay? So this vector is in null space of A, this vector is in null space of A. And x1 hat is in null space of A orthogonal complement. Okay? Now suppose that I distribute this inner product. x1 hat x1 hat plus x1 hat x2 hat plus m, and x2 hat plus m x1 hat plus x2 hat plus m x2 hat plus m. Okay? There are again 4 inner products when I distribute this inner product like this. And sum of those inner products would be equal to 0 because of this property. x1 hat is in null space of A orthogonal complement, and this sum is in null space of A. Okay? Inner product of x1 with x2 hat plus m will be equal to 0, and inner product of x2 hat plus m and x1 will be equal to 0. That means that when I distribute this inner product, I will get only 2 terms, x1 hat plus x2 hat plus m, x2 hat plus m. Cross inner products will disappear because of orthogonality. Okay? And what about this x1 hat x1 hat? It is going to be x1 hat norm square, and I would have x2 hat plus m norm square. Okay? So let me write this like this. X hat plus m norm square can be written as this sum. And you see that, again, I have written this norm square as the sum of 2 norm square. And only one of these norm squares is dependent on the optimization variable m. This norm square is dependent on the optimization variable m, and this norm is always constant. Okay? So that means that whatever I choose my m value, because this norm is non-negative, this norm square is always larger than or equal to this constant. Okay? x1 hat square. I always have this inequality, so this x1 hat norm square is a lower bound for the function that I would like to minimize. And how do I minimize? By choosing an m in null space of A. So this is a lower bound for the function that I would like to minimize. But for this value to be the actual minimum, I need to be able to achieve this value by choosing an m in null space of A. If by choosing an m in null space of A, if I can achieve this value, this lower bound, then I would know that this is going to be my actual minimum. All right? Now the question is, can I make this an equality? Can I make this inequality an equality by choosing an m inside null space of A? Okay? That is going to be my optimal m, which is going to be m star. Okay? Can you make this inequality an equality by choosing an m inside null space of A? So obviously, for this inequality to be an equality, this norm should be equal to 0. Okay? And for this norm to be equal to 0, inside should be equal to 0. The vector inside should be equal to 0. And for the vector inside to be equal to 0, m should be minus x2 hat. Okay? But do you think minus x2 hat is in null space of A? Minus x2 hat. I know that x2 hat is in null space of A. Okay? So what about minus x2 hat? Can it be outside null space of A? The answer is no, because null space of A is actually a subspace. Therefore, if I have a vector in the null space of A, then any scalar multiplication of that vector will be inside null space of A due to the subspace property. That means that I can choose m star equals to minus x2 hat, which is inside null space of A, to achieve this lower bound, which is going to be the minimum value of the function. Okay? So that is our optimal m star. What about the minimum norm solution? So maybe I should erase this part. So what about this x with the minimum norm? It is easy. X, the optimal x star is going to be x hat plus m star, okay? And x hat is x hat 1 plus x hat 2, and m star is minus x2 hat, okay? And these are going to cancel, and I would have x1 hat, okay? So this is the solution of our minimum norm problem, minimum norm solution problem, okay? So what did we achieve here? Minimum a over ax equals to b x. This is my minimum value, okay? x1 hat square. And what about the argument of this minimization? Argument minimum x equals to 1, ax equals to b x hat is nothing but x hat 1, okay? And what is x hat 1? X hat 1 can be obtained by taking an arbitrary solution, x hat, and then decomposing it into two parts. The first part is in null space of A orthogonal complement, and the second part is in null space of A. And then the component inside the null space of A orthogonal complement will be our minimum norm solution. Okay? So x1 hat is equal to, remember this, when I have such a decomposition, these vectors are nothing but the projections of this onto M and onto M orthogonal complement. So here x1 hat is nothing but the projection of an arbitrary solution onto null space of A orthogonal complement. Okay? Projection of an arbitrary solution onto null space of A orthogonal complement. All right? This is quite meaningful actually. Why is that? Remember, non-uniqueness is caused by non-zero vectors inside null space of A. Okay? So in order to obtain a unique solution, unique minimum norm solution, you get rid of all components of an arbitrary solution inside null space of A. You throw away all components of x hat in the direction of null space of A. And then you end up with the projection of x hat onto the orthogonal complement of null space of A. Okay? So you get rid of all components in an arbitrary solution along the directions of null space of A. And the result that you obtain would be the projection of that arbitrary solution onto the orthogonal complement of null space of A. Okay? And that is our minimum norm solution. So now I will go back to the example that we started with, this issue. So back to the example. So remember our example was this, 2x, 2, 1. So B was not inside range space of A. That means I need to calculate B1, which is the projection onto range space of A of B, and this turned out to be 3 over 2, 3 over 2. Okay? And then I need to find the solutions of 1, 1, 2, 2. X hat is equal to B1. 3 over 2, 3 over 2. Okay? And I have found some multiple solutions. One was x hat equals to 3 over 2 and 0. The other one was 0, 3 over 4, etc. Okay, I can find infinitely many solutions here. What is another solution? I can write here x hat is equal to 1 over 2, 1 over 2. Okay, so would this be? So I would have this one, I would have 1 over 2, and I have 1, 3 over 2. Yes, this is also a solution. Now the question is, what is the minimum norm solution? There are infinitely many minimum error solutions. So infinitely many minimum error solutions. So the question is, what is the minimum norm minimum error solution? What is the minimum error solution which has the minimum norm? Okay, that is why I'm going to use this theory here. Okay, what does it tell us? If I take an arbitrary solution, this one or this one, it really doesn't matter. Take an arbitrary solution and then project it onto null space of a orthogonal complement. Okay? If you do that projection, your result is going to be the minimum norm solution of this problem. Okay? So now let us try to do that. I will first calculate null space of A. Null space of A was one-dimensional in this case because range space of A is one-dimensional, and the summation of the dimension of range space of A and null space should be 2, number of columns. Range space of A is one-dimensional, therefore null space of A is one-dimensional. So I need to find only a single non-zero vector inside the null space to find a basis for the null space. Okay? And that single non-zero vector can be 2 minus 1, or any scalar, any non-zero multiple of this vector here. All right? So now, in order to be able to make a projection onto null space of a orthogonal complement, I need to find the orthogonal complement of this null space of A. Okay? And here, look at this expression. Dimension of M plus dimension of M orthogonal complement should be the dimension of the overall space. Okay? Dimension of, therefore, I need to have here dimension of null space of A plus dimension of null space of A orthogonal complement should be what? Dimension of the overall domain here, which is in this case C2, which is in this case 2. Okay? And dimension of the null space is 1. Okay? And this is 2. That means that dimension of the null space of A orthogonal complement should be 1. Okay? So that means that null space of A orthogonal complement is going to be a span of only a single non-zero vector in the same space. Okay? Tell me a non-zero vector which would be orthogonal to any vector here in this null space, in this span. And you see that it is easily the vector 1, 2. Right? So null space of a orthogonal complement would be just this. And the dimension of these two subspaces would be 2, the overall space, because these are in C2. All right? And I would have this as my null space of a orthogonal complement. Now I need to calculate the projection matrix onto that subspace. All right? And then I need to multiply that projection matrix with an arbitrary solution. It really doesn't matter which solution I take. You would always get the same solution at the end. Okay? And so let me try to do it here. So x1 hat is going to be the projection matrix onto null space of a orthogonal complement times an arbitrary solution. So now let us look at projection matrix null space of a orthogonal complement. This is going to be B transpose B. Again, we are working with real vectors. So instead of Hermitian, I can write transpose here. Inverse B transpose. And how should I choose my B? B should be composed of the basis vectors of the subspace that I would like to project onto. And it is this subspace in this case, and in the basis set, there is only one non-zero vector, and therefore I need to write here B transpose B is 1, 2. This is B transpose. So I choose here B equals to 1, 2 here. And B transpose B is going to be 1, 2, and that is going to be just 5. All right? This is a scalar again, because the subspace is one-dimensional. Gramian matrix is 1 by 1, is a scalar. So Gramian matrix, when you calculate it correctly, would always be a square matrix, a square symmetric or Hermitian matrix, depending on the complexity. And it is always going to be a square matrix with size as the dimension of the subspace that you would like to project. Okay? So in this case, dimension of the space that I would like to project is 1. So it is a 1 by 1 matrix. Gramian matrix is 1 by 1. And it is invertible, as you see, because it's non-zero. All right? So now, this means that the P, null space of A orthogonal complement, is equal to B. B is 1, 2. And B transpose B inverse, 1 over 5. And I have B transpose. Okay? And this is going to give me this, 1, 2, 2, 4, and 1 over 5 here. This is the projection matrix onto null space of A orthogonal complement. And then what I have to do is to project an arbitrary solution of this equation onto that subspace by multiplying it with this projection matrix. So that is going to be x1 hat is equal to 1 over 5, 1 over 2, 2, 4, and I have 3 over 2 and 0 here. All right? And this is going to be 1 over 5. I would have 3 over 2 and 3, which is going to be 3 over 10, and I would have 3 over 5. Okay? So this is my minimum norm solution. Minimum norm, minimum error solution. We already calculated infinitely many minimum error solutions, and we have found the one that would have the minimum norm among all those minimum error solutions. So this is the unique minimum error, minimum norm solution. Okay? So if you calculate the norm of this thing, then you will calculate the minimum norm that we can obtain. Any other solution that we have here is going to have a larger norm than that one. All right? So we have found this like this. Now I have calculated already the solution. I will show you only one last thing here. And it is going to be very, very important. And actually it is called fundamental theorem of linear algebra in the area of mathematics. Okay? So here, null space of A was this, and null space of A orthogonal complement was this space. Okay? Now let us go back to this matrix. Do you think this is familiar? This vector 1, 2 here. Now look at this matrix. It is 1, 2, 1, 2. Its rows are actually exactly the same as this basis vector. Is this really a coincidence? So what I mean here is that this A Hermitian for that example is 1, 2, 1, 2, transpose of that matrix. Okay? And we see here that range space of A Hermitian is the column space of this matrix. There is only one linearly independent column, and I have therefore a one-dimensional space, 1, 2 here. This is the range space of A Hermitian. Okay? And this is the null space of A orthogonal complement. All right? So you see that these are the same spaces. Is this really a coincidence? This is really not a coincidence. It is a very, very fundamental fact of linear algebra. And this is actually called the fundamental theorem of linear algebra. And it is a very, very important fact, and that is why we are going to prove this. But actually, I'm going to be I'm going to be showing it on another example to you. Okay? So let us say, let us say that this is my A matrix. 1, 2, 3, 1, 2, 3. Okay? This is my A matrix. Let me look at some spaces in this case. So range space of A is span of these columns. We see that these columns are all linearly dependent. There is only one linearly independent column, which is 1, 1, or 2, 2, or 3, 3. But say this one is linearly dependent with the earlier one, and this one is linearly dependent with this one. So the range space is one-dimensional. Okay? This is my range space. What about the null space of this matrix? So you know, we see that by the rank nullity theorem, dimension of range space of A plus dimension of null space of A is equal to the number of columns here, which is 3 in this case. All right? Dimension of range space is 1. And what about the dimension of null space of A? It should be 2. Okay? That means that null space of A should be just span of 2 non-zero vectors. Okay? And null space of A is in the domain. So I would have vectors with 3 elements in this case. So null space of A is inside the domain. So I need to have 3-dimensional vectors here. All right? So I need to find 2 linearly independent, because the dimension of it should be 2 linearly independent vectors inside the null space of this matrix. So think about an x, and think about that x. When you multiply it with this matrix, it should give you 0. So I can actually find an x as follows: -2, 1, 0, and -3, 0, 1. When I multiply this vector with this matrix, I would get -2 times 1, 1, and 1 times 2, 2, plus 0 times 3, 3. It's going to be 0, 0. And similarly, this one, -3 times 1, 1, plus 3, 3. It's going to be 0 again. So this is my null space in this case. All right? Now let us find the orthogonal complement of the null space. So null space of A and the orthogonal complement of null space of A should live in the same space. So dimension of null space of A plus dimension of null space of A orthogonal complement should be the space of the overall space of the null space, which is R3 or C3. So this is going to be the dimension is going to be 3. Okay? So this is 2-dimensional. As a result, dimension of null space of A orthogonal complement should be 1. All right? Which means that null space of A orthogonal complement is going to be the span of a single non-zero 3-dimensional vector. Okay? Now tell me a 3-dimensional vector which is orthogonal to both of the basis vectors of the null space of A. Because that is what being inside null space of A orthogonal complement means. So I need to find a single non-zero vector which is orthogonal to both basis vectors here of null space of A to find the orthogonal complement of, to find a basis for the orthogonal complement of null space of A. You can here make the following. So just call that vector ABC and take the inner product of it with this one and then with this one, and then calculate a candidate ABC. Okay? You will see that actually is just going to be this. 1, 2, 3, or any non-zero multiple of this one is going to be orthogonal to the first basis vector, orthogonal to the second basis vector. So this span is always orthogonal to the null space of A. Okay? So that is my basis for null space of A orthogonal complement. Now let us look at A Hermitian or A transpose. In this case, since the matrix is real, A Hermitian is equal to A transpose. And it is transpose of that matrix 1, 2, 3, 1, 2, 3. Now let us look at the range space of A Hermitian. Range space of A Hermitian is the column space of A Hermitian. Okay? There is only one linearly independent column, so this is going to be span of just one of the columns, 1, 2, 3. So you see that here I have again the same fact. So null space of A orthogonal complement is equal to range space of A Hermitian. In linear algebra, this is called the fundamental theorem of linear algebra. It is an extremely important fact. And what does this tell us? Null space of A orthogonal complement is equal to range space of A Hermitian. What is range space of A Hermitian? When I take the transpose of a matrix, its rows becomes columns. Okay? When I take the transpose of a matrix, the rows of the original matrix becomes the columns of the transpose or the Hermitian. Okay? So, and what is the range space of A Hermitian? It is the space of columns of A Hermitian. Which means that because these columns are originally the rows, range space of A Hermitian is nothing but the space of the rows of A. Okay? Space of rows of A. So this tells us is here this space that I'm trying to project onto is nothing but the space of the rows of the matrix A. Okay? So what I'm trying to do when I write this projection onto null space of A orthogonal complement except is this. Null space of A orthogonal complement is equal to range space of A Hermitian except. Okay? That means that, and what does this mean? This means that this projection is going to be an element of this space. What does that mean? This means that this minimum error solution is going to be an element of this space. And what does that mean? It means that the minimum error solution is always going to be a linear combination of the rows of the matrix. Okay? Minimum error solution is always going to be a linear combination of the rows of the matrix. In our example, what was our minimum norm solution? In this example, I have found x at 1 is equal to 3 over 5 and I'm making it up, sorry. I have to look at it. So it is 3 over 10 and 3 over 5. 3 over 10 and 3 over 5. Now look at the rows of this matrix. 1, 2, 1, 2. Do you think this solution x1 hat is a linear combination of these rows? Yes, obviously. So here if I multiply one of the rows with 3 over 10 and multiply this with 0, then this is going to be 3 over 10, 3 over 5, and that is going to be like this. So this fact, fundamental theorem of linear algebra, tells us that the minimum norm solution is always a linear combination of the rows of the matrix. Right? Let us write this. Minimum norm solution, because it's a projection onto range space of A Hermitian. Null space of A orthogonal complement is equal to range space of A Hermitian, And that means that the result of this projection should be in this space. And this space is nothing but the row space of the matrix. Minimum norm solution is always a linear combination of the rows of the matrix A. Okay? So here there is one thing that I didn't show you, of course. I want to prove this equality here. That is fundamental theorem of linear algebra. But except for that, we have seen all of the theory so far. So I will summarize the theory in the next lecture. That's going to be all for this lecture. Thank you very much for watching. Bye-bye. Sorry.